Well, good morning, everyone. There's a question I'd like for you to be thinking about. I could get up here and I could talk about a broad range of different topics. I'm pretty sure I wouldn't run out of things to talk about between now and lunchtime. But it's going to be most useful and most relevant if we're able to directly answer the questions, the concerns, the crop challenges that you have and that you're dealing with. So, the question that I'd like for you to think about is, what are the top agronomic challenges that you have that you would love to solve, that you would love to walk out of here today and know the answer to? And I have a few pieces I want to talk about, and then we're going to come back. I'm going to ask you that question. I'm really looking for your input. And I'm going to spend most of this time just in an open Q&A talking about challenges and how to solve them. But before we go there, I really enjoy those types of conversations, and I think everyone does. I've gotten really great feedback from those types of discussions because they're immediately relevant. But often what happens is the conversation ends up going in a direction of focusing on short-term solutions. We have major slug problems, so we put on a foliar application of iron to solve the problem. Okay, well, that's useful information to know, but it doesn't address the deeper systemic question of why do you have slugs showing up in the ecosystem in the first place. So before we get to the Q&A and the problem session, I want to back up a step and speak a bit about the bigger ecosystem challenges of how we should be managing fruit and vegetable production and crop production generally to regenerate our soils. And I'm coming to this conversation inspired by a very in-depth conversation that I had with Christine Jones from Australia a couple of weeks ago, and a fresh appreciation for the power of a diverse microbiome, the likes of which most of us have never gotten to observe. I constantly remind us that most of us have never gotten to see what really healthy plants actually look like. Most of us don't get to experience crops that are completely resistant to diseases and to insects based on their nutritional profile and based on their microbiome. It's a lot of fun when we get to see it, but most farmers have never experienced that. And in a parallel to that, most of farmers also have never gotten to see what an abundantly healthy soil microbiome looks like as well. So I want to offer some context. Some of the pieces that I learned in the conversation with Christine Jones a couple of weeks ago. First, I'm going to back up one step before that. Why is the microbiome important, and why should we be thinking about managing nutrition from a biome perspective? There are two models of plant nutrition that are widely recognized today. One of them has been the established model for the last century, and this is the model of plants having the ability to absorb nutrients from the soil solution in the form of simple ions. So in the soil's water solution, we have calcium ions, potassium ions, magnesium ions, and so forth, that plants have the ability to absorb these ions directly from the soil solution. So this is the model that has been used in mainstream agronomy for the last 100+ years. But there is a second model of agronomy, or second model of plant nutrition, which is that plants have associated beneficial microorganisms that colonize the entire plant. They live inside the plant in every single organ. They are in the seed, they're in the fruit, they're inside the leaves, they're on the leaf surface, they're throughout the entire root system, and they surround the root system on the exterior of the root system, where we call it the rhizosphere. And this associated microbiome has the capacity to extract and etch minerals from the soil mineral profile and then transports them inside their bodies, whether we're talking about bacterial species or fungal species. They transport these nutrients inside the plant, and then the plant uses the entire microorganism as a source of nutrition. This is the way real-world nutrition actually works and has worked for millennia. These trees and the plants that we're surrounded with that are not being fertilized are absorbing, based on the very early stage and limited data that we have at this point, it appears that most wild ecosystems that are not being fertilized are absorbing less than 5% of their total nutrients using the model of simple ions. And this has been a question that I've had in my mind for a couple of decades. We have about less than 10 miles from where I now live is where the glaciers dropped a lot of the rocks when the glaciers melted. And so we have this rock-strewn terrain, really large rocks and cliffs, small cliffs, where we have trees growing out of bare rock. There is no soil. There is no topsoil, nor has there ever been topsoil where these trees are growing. And yet you have trees that are sized similar to the ones that we're sitting under, and their growth rings are the exact same size as trees that are growing in fertile topsoil. So they are not suffering from a nutrient deficiency. Where is their nutrition coming from, and how are they getting it? That was one of the questions that I had in the back of my mind, that I've had in the back of my mind for quite some time, that led me to understanding how critically important the microbiome is. So, how many of you have heard of or are familiar with this concept called the rhizophagy cycle? Okay? You're about to get, this is mind-blowing. The rhizophagy cycle is a lot of fun. The first papers on the rhizophagy cycle were published approximately 17 years ago by the lead researcher was an individual named Dr. James White from Rutgers University. He has collaborators that he's now worked with around the world. And in the rhizophagy cycle, he and his colleagues were able to document and to describe exactly how plants get nutrition from microbes. And I want to talk about this because it's fundamentally important to a different model of agronomy and a different model of plant nutrition. So what they identified is that plants, as plant root tips grow through the soil, the root tip is actually quite porous. It has a sponge-like consistency and has the ability to absorb entire bacterial cells into the root tip. And bacteria, particularly these associated endophytes that colonize the entire plant system, concentrate at these growing root tips because that is where the food source is the most concentrated, because the plant is transmitting sugars out to these growing root tips. So there's an environment with an abundant food source with lots of sugars right at the growing root tips. And we have these large bacterial colonies that measure in the thousands or tens of thousands that are right on the root tip surface itself. These bacteria are then absorbed into the root system, and in the first couple inches, immediately after they're absorbed, the plant exposes them to high concentrations of nitrous oxide and free oxygen radicals and oxidizes their cell membranes. So now that strips off the cell membrane of the bacteria. Now you essentially have a naked bacterial cell. These naked cells, as well as some cells who survive this process and still have the cell membrane, are then transported through the plant to every location inside the plant, and the plant cells actually absorb the entire bacterial cells and utilize them as a source of nutrition. It's a pretty incredible process. But it gets even better. After the zone of the first couple of inches behind the growing tip, some of these bacterial cells begin to congregate and begin to accumulate in that area. And as they begin accumulating, they trigger the formation of root hair. And these root hair, as the root hair develop, these bacterial cells, including a large number of naked cells, now move out through the root hairs back into the soil environment. And the plant doesn't just release these bacterial cells, but it also releases mucilage and compounds that allow the cells to rapidly reform their cell membranes. So it is actively propagating and supporting and helping these bacteria. In addition, as these bacteria have made this short journey through these couple inches of root system, the plant is also communicating with them with electrical signals and chemical signals, and it's communicating to them exactly what its nutritional requirements are. It's telling them, hey, I need more zinc, or I need more manganese, I need more calcium. These bacteria go back out into the soil environment, and they spread that message through the rest of the soil community through a process called quorum sensing. And it's incredibly It's amazing how rapidly this can happen. When you have microorganisms that are transmitted, when they have this information about what the plant's nutritional requirements are, they move out of the soil or out of the plant root hairs. They begin communicating that message. In 4 hours, the entire soil microbiome, down to a depth of 4 feet, begins selectively absorbing and sequestering and extracting more of that specific mineral that the plant needs in 4 hours, the entire associated microbiome. Now, these bacteria that are loaded with the additional zinc or the additional manganese move through the fungal hyphae network of mycorrhizal fungi and other saprophytic fungi, and also the bacteria right at the growing root tips now have higher concentrations of the minerals of the plant that the crop requires, so the crop now has access to more of the nutrients that it needed in a matter of 4 hours after it first released the signal. Isn't this an incredible process? Plants are farming and communicating with and have an active symbiotic relationship with bacteria and fungi and other soil microorganisms. They in some ways, I've used the analogy, I actually don't like the analogy so well, but it makes for an awesome joke. I've said that plants are farming bacteria like we farm livestock. And that also means that plants are not vegetarians. So, tomorrow, I'm not going to be able to be here tomorrow, but tomorrow Aaron is going to talk about nutrient density and what it means to grow medicinal quality food. And medicinal quality food, from a growing perspective, 2011, I think, or 2011, I first put out the concept of a plant health pyramid and the different stages of health that occur inside a plant based on the physiological processes. The peak of the plant health pyramid, level 4, is when plants become completely resistant to all diseases and all insects. And it's also when they have the best flavor and the best quality. And we can start having a legitimate conversation about growing food as medicine. And in order to get to level 3, from a growing production perspective, requires 3 things. First, it requires soil that has an available mineral nutritional profile. And the word available is an important qualifier. We're going to come back to this because I just described how soil biology functions to make nutrients available, as long as they are present in the native geological profile to begin with. There are parts of the country where plants will never have enough selenium or enough molybdenum or enough cobalt because it's not present in the parent bedrock material, it's not present in the soil profile, and therefore that needs to be, some of those minerals will need to be added or adjusted. So that's the first requirement for growing medicinal quality food, is a solid mineral nutritional foundation. Second is an abundant and diverse microbiome that can supply the majority of the crop's nutritional requirements. The healthiest, highest quality, highest yielding, best performing crops I've ever observed were crops where the soil had no fertilizer applied to it for long periods of time. And when I say no fertilizer, I'm not just talking about fertilizer in a bag. I'm talking about significant manure applications or compost applications or growing legume cover crops. We're going to come back to that. I'm going to talk more about the challenges of legume cover crops. Prepare to be surprised. So those are the first 2 requirements: mineral nutrition and abundant, healthy microbiome. And the third requirement is the right genetics. It's possible, we had some of this conversation on our way here this morning. What's the word that I'm looking for? Some plant genetics, often associated with heirloom or older style genetics before intensive breeding pressure, but there are some modern varieties that also have this capacity. Various genetics and various varieties have a differing degree of ability to have this symbiotic relationship with the microbiome. Some of them are much better at it than others. And as a result, some of them are much better at producing phytonutrient-dense food. So poor seed genetics, poor variety selection cannot overcome, how can I say this accurately? You can have the absolute ideal soil from ideal soil minerals, ideal soil microbes, but plant poor genetics on it and not produce a nutrient-dense crop. So plant genetics can supersede optimal soil health. And there's also an element, not to the same degree perhaps, but there's also an element of the reverse being true. When you have really good plant genetics, they can overcome challenging soil conditions to some degree. All right, so the piece that I think, the piece that I've learned in the last couple of weeks is a fresh appreciation for the sheer horsepower that can be brought to bear when we have a vigorous, healthy, and active microbiome, and how few of us have actually gotten to observe and experience that, and why we don't get to experience it. Elaine Ingham and other microbiologists for the last 4 decades have been saying that when you have a soil that has an abundant microbial population, the microbial population will alter the bulk soil chemistry. It will change the mineral profile. You can have soil that perhaps has an acidic pH and doesn't have adequate calcium, and when you rebalance the soil microbial profile, it will increase calcium levels and it will increase pH, and the soil will self-regulate and self-optimize. Many farmers have tried that and have failed. But it does work sometimes because we have seen it. We have the data to support that it does happen sometimes. I've seen soils go from 30% base saturation calcium at 600 parts per million to 1800 parts per million, and from an acidic pH of 4.5 to a pH of 6.2 without adding a single drop of calcium. So it happens sometimes, but why didn't it happen all the time? I now think I know part of the answer, perhaps a large part of the answer. And actually, before I give you the answer, I want to add one additional piece of context. I've also learned there is this, the conversation around how we talk about soil carbon and soil organic matter is constantly evolving. We're now, the language around humic substances and humus formation is the scientific language is very different from what it was even 15 years ago or even 10 years ago. We're now having a conversation around microbial necromass, dead bacterial and fungal cells. And as we understand how organic matter is being, better understand how organic matter is developing, is being cycled, it becomes clear that we have two completely, well, it's not quite accurate to say two completely different systems, but yet we have two subsystems that function very differently. We have the top 6 inches of the soil profile, where it's comparatively easy to build organic matter quickly in the top 6 inches, and also comparatively easy to lose it. The carbon and the microbial necromass in those top 6 inches cycles very quickly. And that is actually, as long as we have green growing plants there to capture the carbon that is being released, we want to cycle carbon quickly. We want to cycle as much carbon. The highest yielding soils are soils which cycle carbon rapidly. They release carbon back into the atmosphere as carbon dioxide, where we have green growing plants that are capable of capturing it and incorporating it back into the plants. We don't lose any from the system, we simply cycle more. And in fact, we bring in more than what the soil is losing. But the top 6 inches cycles very quickly, or it should. But from 6 inches to 40 inches is a completely different story. Here is where we can build soil organic matter that is stable for the long term, and that builds very strong soil aggregates, and that supports an abundant fungal and bacterial population at depth. How many of you have seen soils that had a friable chocolate cake texture, that had good soil aggregation down to a depth, I'm going to say below 10 inches? How many of you have seen that? Not a single hand. I've seen it several dozen times, but considering the number of farms, the type of farms that we work with, I should have seen it hundreds or thousands of times at this point, and I haven't. And I finally, with Christine Jones' wake-up call, I'm starting to figure out why, I think. And the why is because of two problems. Problem number one is that we do not have enough microbial diversity because we don't have enough plant diversity. And problem number two is because we have excessive nitrogen in our systems, even in many of our organic and regenerative systems. So I had a conversation on the podcast with Helen Athow, regenerative orchardist and vegetable grower, probably a year ago, where she described, and this has been a common refrain for many growers, she described how early on in her career, or as a farmer, she was concerned about supplying enough nitrogen, and after half a dozen years she came to the realization that in fact her problem was supplying enough carbon. And now she's constantly trying to supply more carbon to her soils and to her ecosystem, and as she supplied more carbon, her need for nitrogen disappeared. She no longer needed any additional nitrogen. Oh boy. I need to talk about a sidebar a little bit here. This is an important sidebar. Why? Let me make sure I keep my train of thought here. So I'm going to put a bookmark into building soil diversity, microbial diversity with plant diversity. I want to come back to that point, but I want to talk a bit about nitrogen and organic ecosystems and the power of the microbiome. There's an individual who some of you may know not too far from here, Walter Goldstein from the Mondawmin Institute in Wisconsin, has been selecting corn varieties for the last 20 years that were kind of origin genetics coming from Mexico that had the ability to, he believed, to fix nitrogen 100 and supply 100% of the crop's nitrogen requirements. So I was able to facilitate a connection between Walter and James White, and they were able to identify that first, corn seed generally, most corn seed that hasn't been compromised, each seed contains 9 billion with a B microbial cells inside of it. So we need to start thinking about seeds as microbial inoculants. They are vectors for microbial populations. And Walter spent 20 years propagating and developing his different varieties and developing different parent seed lines in an environment that was deliberately nitrogen deprived. He grew them in soil that was being managed with biodynamic systems, but there was no compost applied, there was no manure applied, and there were no green manure cover crops grown on that soil. He was very specifically, very deliberately selecting these varieties to grow in a nitrogen deprived environment. And as it turns out, when Dr. White started researching the microbiome on his seed specifically, it turns out that the endophytes, the bacteria that are living inside this corn plant, both inside the plant, on the leaf surface, around the root system, have the ability to fix 100% of the crop's nitrogen requirements. And if you want to shut that system down, it's very easy. You give the plant a taste of nitrogen, boom, it's gone. And by the way, that is not just synthetic applied nitrogen, that is also free nitrogen in the soil profile from a legume cover crop. So if you grow a cover crop of peas or beans or hairy vetch, and you plow that down and incorporate it into the soil profile, you don't even have to incorporate it, just the nodules in the soil profile itself. If you plant this corn into that type of an environment, it will lose some of its ability of the endophytes to, I shouldn't say it'll lose the ability, but the ability will be shut down because it's unneeded, it's unnecessary. The plant doesn't need to supply carbohydrates to those organisms. One of the things that's been known for a long time is when we grow soybeans, a corn crop tends to build soil aggregate structure. Soybeans tend to collapse soil aggregate structure. We lose soil aggregation, we lose soil structure when we grow soybeans. And the reason for that is because soybeans are a legume, they provide nitrogen to the system, and they burn carbon out of the top 6 inches. So when you grow a soybean crop, you will lose carbon out of the top 6 inches of your soil profile, unlike when you grow corn. And it's because of this nitrogen fixation effect that comes from the rhizobium. So now, in the context of when we think about each seed as when we think about seeds as being a microbial inoculant and having a packet of all these associated endophytes, the microbial population in the soil is a remarkable case of 1 + 1 not equaling 2. When you have these compounding effects of diversity of different microorganisms that they enter into these relationship of communities and begin engaging in quorum sensing. This could be another earthworm hole. I don't have a clock. How are we doing on time here? Thank you. So I don't have time to go into quorum sensing in detail, but let me say it very simple. Many of you are familiar with biofilms, I would expect. So a biofilm is when one particular organism establishes a large enough population that it begins engaging in quorum sensing. So what happens in quorum sensing is that, first of all, it requires a large enough population to reach a critical threshold. When you have a large enough population to reach a critical threshold, before that point, every individual organism behaves as a unique individual. It has to do everything. It has to protect itself from the environment. It has to feed itself, get enough of a food source. It engages in all functions, whatever is required in the environment, all the time. Once the population becomes big enough and crosses a critical threshold, they begin engaging in quorum sensing, where the community starts behaving as one organism. So now you have some cells, the cells on the exterior, begin shielding the population from the environment. The cells on the interior engage in immune system type processes and developing immunity. So all of a sudden there's this differentiation of duties. No one does everything anymore. Instead, each individual cell only does one specific thing or a few specific things that the superorganism of the whole community needs. Now, in the case of biofilm development in our bodies or that cause infections, these infections and these biofilms are developed develop into a superorganism of one specific microbial population. But in soil, you can get quorum sensing and quorum populations that constitute hundreds of species. The entire community, the entire population is in constant communication with each other once they cross this critical threshold. And when they do that, their entire behavior begins to change. Now, mycorrhizal fungi start doing only some things really, really well because they don't have to do other things. Maybe mycorrhizal fungi no longer extracts phosphorus so well because there's this bacteria over here that is a part of the community that does phosphorus extraction particularly well. So there is this synergistic effect where once the population becomes large enough, their entire behavior changes. Most farmers have never gotten to observe or experience this because their microbial population never got big enough in the first place to establish a quorum community. And part of the reason why it never got big enough, and part of the reason why most soils don't support a microbial community that is in a quorum sensing mode. So when we think about a seed as a vector for different microbial populations, we understand that each plant has its own associated microbiome. And Christine Jones pointed out that we need to think of the microbiome that is associated with different plants, not just in terms of the individual species, but in terms of overall plant groups and plant families. So the microbiome of milo and sorghum Sudan grass and corn is too similar. There are too many overlaps to consider that as three separate species from a microbiome diversification perspective. in reality, we need to begin thinking about different plant groups and different plant families. And in her 30 years of experience and observation, she suggests that it takes at bare bones minimum diversity of at least 4 different plant groups to have a large enough, diverse enough microbial population to establish a quorum sensing able microbiome that are present in the same soil environment. At least 4 different plant groups, and preferably more. In particular, one of the plant groups that is largely missing from modern day agriculture and that has particular value in building soil carbon at depth are the various groups of forbs. So what are forbs? Forbs are broadleaf non-grasses, essentially. And by the way, this is not a conversation about annual plants versus perennial plants. Annuals also bring a lot of value here. But she described how, in her research, the plant species and species combination, which develop soil aggregation to a depth of 40 inches and develop these amazing soil profiles, were dominated by forbs, not by grasses, and most certainly not by legumes. In fact, in her estimation, legumes could be less than 5% of a population and perhaps even not present at all in order to have these deep soil building effects and benefits. And as I started thinking about, I was part of a group conversation, and several members of the group started asking about grasses, and to just kind of the inherent assumption was that, well, we need to include more grasses in the system because it is the grasses that have these deep root systems that have the ability to build soil organic matter and produce soil aggregation in the deep profile. And there was an immediate no, absolutely not. It is not coming from grasses. You know, it's interesting how we tend to credit what we can see visually, and we think about these grasses that have these large root systems, and we think because they have a large root system, therefore they must have a great deal of benefit. When you think about a forb, a couple of plants, you're all familiar with chicory or some of the thistles. What do their root systems look like? They have a taproot type root system, unlike a grass. Yet, when in some of the limited research I've been able to find where we look at carbohydrate partitioning, how much of the carbohydrate in these plants goes down to the root system versus staying on top, the ratios for the forbs and the grasses and the other plants actually looks quite similar. So forbs are also sending, depending on the stage of plant growth, vegetative versus reproductive stages, they're sending anywhere from 50 to 70% of their total sugar production every day out through the root system. But they have this skinny taproot type root system, so where does the sugar go? The answer is, it doesn't stay in the root system. It goes out through the roots as root exudates. And that is why forbs contribute so much more of their carbon to the soil microbial profile, and that is why they are particularly useful in building soil carbon and causing strong aggregation at depth. Now, if we come back around the mountain, I could talk more about this topic, but the reason I wanted to talk about this is because I'm persuaded we can have a conversation about how to use foliar sprays to solve disease and insect problems with nutrition management. And it's necessary for us to have those conversations because some of us may go home and we have a Japanese beetle problem on a certain crop and we need a solution for it right now. Those solutions are very necessary and beneficial, but at the same time, we need to understand how do we change our systems so that we prevent these problems systemically and we're not dependent on foliar sprays in the long term. That's what we really need to be thinking about. And the answer to that, in my assessment, is that we need to bring into our soils, and we need to establish this very rich, deep soil microbial population that has the ability for quorum sensing that can supply all of our crops' nutritional requirements. When that happens, the need for foliar applications and spot treatment band-aids goes out the window. So, how do you do that? Christine made a couple of other comments and points that I think were very interesting, particularly for us as a group. If you're mostly interested in fruit and vegetable production, there are a few pieces that are very relevant. When thinking about species diversity of plant groups, the microbiome effect will carry on after the death of a crop for a period of time. She made the point that when we have cover crops that winter kill, let's say we plant buckwheat or radishes or a diverse cover crop mix in the fall, and some of those species winter kill during the winter months, the microbiome that they are associated with will carry through into the spring and benefit the following crop that we plant the following spring. So we can consider that as a part of our contribution to the microbiome diversity. However, that microbiome associated with a specific plant will degrade over time, and obviously the speed at which it degrades is going to be dependent on soil temperatures and the rest of the microbial population and how rapidly that develops. She said something else that was quite interesting, which was there's this intense debate in the organic and the regenerative cropping world of which is the most damaging to soil, tillage or herbicides. And I'd like to ask, where's option 3 and option 4? The world is bigger than just those two options, but that's a conversation for another moment. Many people, and there's even some published and some unpublished research here in North America that indicates that herbicides have a less damaging effect to the soil profile than tillage. And yet there are other people who strongly, adamantly hold the view that that is not the case. And Christine holds the view that tillage is significantly less damaging to the soil profile than herbicides, and she has dozens of papers and a lot of data that is unpublished to support that. But she is also approaching this from a very different perspective and a very different experience from the way that most of the research and the context in which most people are thinking about it. Her context and what she's thinking about is she's saying, okay, we want to have a healthy soil with an abundant microbiome population and good soil aggregation to a depth of 40 inches. When we have good soil aggregation to a depth of 40 inches, then tillage treatment in the top, there's actually an important point here. She's suggested that when you till the top 6 inches of soil and you immediately plant back into it, so you have immediate colonization of living roots again from a diversity of plant species, that does not have a detrimental effect to the total soil microbial community because you have this tremendous reserve of 32 inches or 34 inches that was never disturbed, and it's going to immediately colonize those top 6 inches again, and there is not even a hesitation in the microbiome community in its continued propagation. But that's the key phrase: immediate replant with a diversity of species. Whereas her data with herbicides, and particularly she said the compounds that do the greatest damage to soil are fungicides, even more damaging than herbicides. Why? Because when they were measuring the impacts of fungicide treatments led to the complete loss of soil structure for the depth of the entire 40-inch profile, because that soil aggregation down at that depth was a function of soil fungal populations that were triggering strong aggregation and developing strong aggregate stability. So while tillage had a temporary impact on the top 6 inches, fungicides and also herbicides to a lesser degree had a much more permanent impact to a much deeper layer of the soil profile. So something to think about. Yeah. All right. Where's the boss? He disappeared.